3.1, we're going to look at extrema on an interval. So first of all, let's talk about what we mean by extrema. So let's suppose we have an interval from A to B, and we have some function. Let's call the function f. Then the extrema are just the largest and smallest values, the maximums and minimums. So for example, on this interval, we have a maximum at B, we have a minimum at A, and the maximum value is the value of our function at B, not the x value itself, but the y when we plug a B into our function. And the minimum is f of A. What is the corresponding y value at that point? Now, occasionally, we might have an interval that doesn't have a maximum or a minimum. And that is going to be if those points where the maximum or minimum would have occurred, if those are not included. So this interval is actually considered an open interval, meaning that it does not include these endpoints, that the interval is listed with parentheses. So notice where the maximum would have occurred, there is no point there. If we think about what's happening as our function gets closer and closer to that point, it's getting higher and higher and higher, but it never reaches that top point, which is kind of an odd thought that it doesn't go up to infinity, but it keeps on growing forever. The closer we get in the x direction, we're getting closer and closer to that highest y value, but we never quite make it. So we have no maximum here. Likewise, where the minimum would have occurred if we included that point, since that point doesn't exist, this one has no minimum. Now, of course, sometimes our maximums and minimums may occur inside our interval. If we have a curve that does something like this, the maximum value on our interval is at B, but the minimum value of our interval is somewhere in between. Let's call that C. So our minimum is f of C. Now, if our for our closed interval, if our maximum or minimums do not happen at the end, then there must have been a place that we went down and went back up, or conversely went up and went back down. So we would have a max here, or in this case, we'd have a min here. And if we look at what our tangent line would be doing, if you think about being on top of a mountain, it's where if you went from one side, you were going up, and then on the other side, you would be going down. So if you're sitting at that peak, and you would be increasing on this side, decreasing on the other side, then you would have a slope of 0 at that peak. Same thing down here. If this is the minimum value, then our slope would be 0 there. Now there is an exception to that. If we have a curve that's not really a smooth curve, if we have something like this, then at that point, our slope is undefined. If we think about our tangent lines, let me move this down a little bit. Not flip it. If we move that down a little bit, if we were to draw tangent lines coming from the left side, it appears that the slope at that point is positive. But if we draw tangent lines coming from the right side, it appears that our tangent lines are negative. So who's to say which one of those is it? Is it like that? Is it like that? There are lots of tangent lines that we could draw to that specific point, so we can't really define our slope. So we would say that our first derivative at that point is undefined. The first derivative does not exist at that point. On these other ones, the first derivative is 0. So these are what are known as critical points or critical values, where our first derivative equals 0, or where our first derivative is undefined. So when we're looking for extrema on an interval, whether it's an open interval or a closed interval, we do want to look to see if we have critical points, because those are possible locations of extrema. If we sketch a curve, let's add a little bit more terminology. This point here is a maximum, but notice it's not the highest point on the entire graph. If you compare this point to the points around it, it's considered a local maximum. In its location, it's higher than points near it, or sometimes books refer to it as a relative maximum. Relative to its neighbors, that point is higher than all the other ones. Likewise, this point is a relative minimum or a local minimum. Notice neither one of those are the highest point or the lowest point on the entire graph. This graph keeps on going up forever and down forever, so this is not the absolute max or the absolute minimum. They're just relative to their area. They're the maximums or minimums. So we're going to look at closed intervals to begin with. So that means that we're looking at an interval that includes the left and the right side. So if we want to find out the absolute maximum and absolute minimum, we're going to check the y value at each end to see which end is the highest and which end is the lowest. And then we're going to look for any critical points in between, because if there is a point that's higher than the highest point, than the highest end, or lower than the lowest end, it's going to occur where we have a critical point, where our first derivative is either 0 or undefined. Now, these are specifically for functions that are continuous on our interval. If we have a function that is not continuous on our interval, then there could be other things that happen. But if our function is continuous from A to B, then these things are true. The maximum occurs either at the left endpoint, the right endpoint, or at a critical point in between. Now you might say, well, why is that based on continuity? If we look at an example where we have a function that's not continuous on the whole interval, we might have, let's say, a vertical asymptote somewhere in between. That goes up forever on both sides of it. So our maximum is not here or here, and in fact, that doesn't have a maximum in that interval. So let's work through an example or two. Let's suppose we have h of x equals 5 minus 2x squared, and we want to look at the interval from -3 to 1. So let's notice this is a closed interval, so we're including each endpoint on our curve, and it's continuous. So let's look at the y value on each end. So on the left end of our curve, if we put in a -3, -3 squared is 9. 2 times 9 is 18. So we get -3. 13 as our y value when x is negative 3. If we put in a 1, 1 squared is 1 times 2. 1 times 2 is 2. So we get a y value of 3. So just looking at the endpoints, the right end is higher than the left end. But if there's a higher point than the right side or a lower point than the left side, then it's going to occur at a critical point. So we need to get our critical points. So we take our first derivative. The derivative of a constant is 0. If we take the derivative of the second term, we bring our 2 down, x to the 1 less power. So our critical points occur where that is either equal to 0 or undefined. Notice since that's a polynomial, it's not going to be undefined. So if we set it equal to 0, divide both sides by negative 4. So we have a critical point at 0. Is 0 in our interval? Our interval goes from negative 3 to 1, so yes, 0 is inside our interval. So we need to find out what is the y value when x is 0. So if we plug in a 0, 0 squared is 0, 2 times 0 is 0. So our y value when x is 0 is 5. So if we compare our y values on each end and the y value at our critical point, this is the highest y, this is the lowest y. So this is our largest value, our largest y value inside our interval, and this is the smallest y value inside our interval. Now notice when we got our critical point, we plugged it into the original function because we're looking for the y value. We found the critical point by setting the derivative equal to 0, but if we're looking for a y value, we plug that x back into the function. So if we were just to quickly sketch this, and we're not going to do it get too accurate here. When x is negative 3, we're way down here. When x is 0, we're up to 5. When x is 1, we're up 3. You might have noticed this was an upside down parabola. It's a parabola because it's a quadratic function. It's upside down because this coefficient is 0. So yeah, that's where our maximum occurs. We have a maximum of 5 when x is 0. We have a minimum of negative 13 when x is 0. So let's do another. Let's see. And here, let's use the interval negative 1 to 1. So let's find g of negative 1. So if we put in a negative 1, keep in mind what this exponent tells us to do. It says to take the cube root of negative 1 squared. So we could either square the negative 1 on the outside or square the answer on the outside, or we could square the negative 1 on the inside. So power and root. Well, if we square negative 1, that's going to be a positive 1. The cube root of positive 1 is 1. So we get 3 times 1 minus 2 times negative 1. So g of negative 1 is 5. So the left side of our interval is at a height of 5. Now let's check the right side of our interval. If we put a 1 into our function, we have 3 times 1 to the 2/3 minus 2 times 1. Positive 1 to any power is 1. 1 times 3 is 3. Negative 2 times 1. So when x is 1, y is 1. So if we have a higher point than the left side or a lower point than the right side, it's going to have to occur at a critical point. So we need to take our derivative and find when is our derivative 0 or when is our derivative undefined. So if we take the derivative of the first term, 3 is a coefficient, we bring the exponent down, and then we do x to the 1 less power. Well, 1 less than 2/3 would be 2/3 minus 3/3, so that's negative 1/3. And then the derivative of 2x is 2. So notice this 3 and this 3 cancel, so we have 2x to the negative 1/3 minus 2. But let's simplify that a little bit. That might make finding our critical value a little bit easier. So we have a negative exponent, so let's take it to the denominator. And let's call that, let's see, that'll be x to the positive 1/3 on bottom. So let's call that the cube root of x down there. It would be best if we had a common denominator here. So let's get a common denominator by multiplying top and bottom of the second term by the square root of not 3. The cube root of x, I'll say it right in a minute. This is the cube root of x to the first. So the cube root of x. So we have both fractions have a cube root of x on bottom. So on top we have a 2 minus 2 cube roots of x. So that's our first derivative. So we need to ask ourselves two things. When is this undefined? In order for this to be undefined, that will occur anytime the denominator is 0. Well, if we cube both sides, then in order for the cube root of x to be 0, that would be whenever x is 0, which is inside our interval. All right, now let's look at finding out when is our first derivative equal to 0. We found out where it's undefined. This is where our first derivative is undefined. Now find out when is it equal to 0. We've discussed in class, if we have a single fraction, a single rational expression, in order for a fraction to be equal to 0, that would be 0. Because 0 divided by anything is 0. So let's take our numerator and see when is our numerator equal to 0. So we can add 2 cube roots of x to both sides. We can divide both sides by 2. Gotta go right in that 3 again. So we get 1 equals a cube root of x. If we cube both sides, we get x on the right, 1 on the left. Well, notice that's a critical point, but that's also the right side of our interval. So we have already found the y value, value of 1. So our critical points inside our interval are x equals 0 and x equals 1. So let's find out, well, what is the y value when x is 0? So if we plug a 0 into our function, 0 to any power is 0, times 3 is 0. 2 times 0 is 0. So when x is 0, y is 0. So the y value on the left is 5, the y value on the right is 1, the y value at our internal critical point is 0. So this is the lowest, this is the highest, so our minimum and our maximum. Now let's discuss what our minimum and maximum would be if we slightly closed or changed our interval. If we change this to an open interval, let's say we make the left side open, so we're not including -1 anymore. We're getting really close to it, but we are including 1. Well, our minimum occurred at 0. We didn't take 0 away, so we still have a minimum there. Our maximum occurred when x is -1, but we don't include that point anymore. So in this case, there would be no maximum. Our minimum would still be at 0. If we did it the other way, if we included the left side, but we didn't include the right side, well, taking away the right side, notice that does not take away a maximum or a minimum value for the interval. 1, when x was 1, that was neither the highest or lowest value inside that interval, so we didn't get rid of the maximum or the minimum. So if we have an interval and the ends are not included, we want to essentially find the maximum or minimum on the closed interval and then ask ourselves, if we change that to a parenthesis, is that going to get rid of the maximum? Is that going to get rid of the minimum? Or do we still have both of them? All right, let's do another. Let's look at f of x equals the square root of 4 minus x squared. And let's find the extrema on the interval -2 to 2. -2 to 2 open on both ends, and 1 to 2. So let's find the extrema on each of these intervals. So to begin with, let's evaluate the function at some values. Let's evaluate it at -2. So if we substitute a -2 into our function, -2 squared is 4. 4 minus 4 is 0. If we substitute a 0 in, 0 squared is 0. 4 minus 0 is 4. The square root of 4 is 2. Let's see, if we put a 1 in, 1 squared is 1. 4 minus 1 is 3. So that's the square root of 3, which as a decimal, the square root of 3 is about 1.7. And then let's plug in a +2, and that should take care of all of the values on the edges of our intervals here. So if we plug in a +2, 2 squared is 4. 4 minus 4 is 0. The square root of 0 is 0. So that takes care of all of our edges. Now we need to look to see if we have any critical values inside any of these intervals. So let's begin by rewriting our function in exponential form. So if we're taking a square root, our root is 2. We have that base 1 time. So we're going to have to use the chain rule to take our derivative. So the chain rule says to take the derivative of the outside. So on the outside, we have something to the 1/2 power. So we bring our 1/2 down to the 1 less power. 1 less than 1/2 is -1/2 times the derivative of the inside. So the derivative of the inside is -2x. So that 2 and that 2 cancel. Let's rewrite this as -x. Since this has a negative exponent, we need to take it to the denominator. And if we have something to the 1/2 power on bottom, we can call that the square root 4 minus x squared. So that's our first derivative. Now, if we want to find our critical points, this first derivative is going to be 0. going to be 0 anytime that the numerator is 0, but that numerator is 0 when x is 0. So that's a critical point. Our derivative is going to be undefined anytime the denominator is 0. So if we set the denominator equal to 0, square both sides, so we get 0 equals 4 minus x squared. We can move the x squared over, take the square root of both sides. So if we take the square root of both sides, we include plus or minus. So those are also critical points. The first one is a critical point where our first derivative is 0. The other ones are critical points where our first derivative is undefined. Look at these piece by piece. So if we look at the interval from -2 to 2. So at -2, our y value is 0. 2, our y value was 0. And then we had a critical point inside that interval when x is 0. So if we put a 0 in for x, we got 2. So this is the largest value, that's the maximum on that interval, and both of these are minimum values for that interval. All right, so part A is from -2 to 0. So at -2, remember, our y value is 0. At 0, our y value was 2. But remember, we don't include that. If we look at the whole interval, we had minimums at -2 and 2. Well, we still have -2 included, which is a minimum. We had a maximum at 0. Well, 0 is no longer included, so there is no maximum for this interval. So that interval has no maximum because where the maximum would have occurred, that point is not included. All right, so part C. Part C does not include the edges. Well, when we did the closed interval, we had a minimum at both ends. And that was the only place we had a minimum was at the ends. Since the ends are not included, we have no minimum. Our maximum was at 0. 0 is still inside our interval. So we have a max of 2 when x is 0. Remember when we plugged a 0 in for x, we got a 2. So that is the largest value in our interval, but we don't have a lowest value because where the minimums would have occurred, those points are no longer there. And then D says to include 1, don't include 2. So at 1, that's where we had a square root of 3. Let's think about this. On the interval from -2 to 2, 2 was one of the minimums. That was one of the lowest values. This is essentially a subinterval of that one. So likewise, where the lowest point would have occurred would have been at 2. Since 2 is no longer included, there is no minimum. Also, notice that x equals 0 is not in our interval, so at x equals 0, that is not going to be our maximum. Our maximum is going to be the highest of the two ends. The left end, when we put 1 in, we get the square root of 3. Remember the right end, when we put 2 in, we got 0, but we don't include that one anyway. So this is the higher of the two. There is no critical point in between there, so that must be the maximum value on that interval. Where we would have had a minimum would have been the right side. That's not included, so we have no minimum. So let's explain that one more time. If we check the edges, and remember for this interval, there is no critical point inside the interval 1 to 2. So if there is no critical point, then the only places that we can check for maximums or minimums will be on the edges. So when x is 1, we got root 3. When x is 2, we got 0. So this would have been the maximum, this would have been the minimum if we would have included the right side. But since we don't include the right side, there is not a point where the minimum is, so there is no minimum. There is a point where the maximum would be, so there is a maximum. All right, so that's just an overview of 3.1. That should be enough to get you kind of started on there.